Hey everybody, Joel Robinson here, and have you ever wanted to build something truly from the ground up? Something that seems almost like magic to most people? Well, that's what we're tackling in this video, building an operating system. I know what you're thinking. Joel, this is some seriously next-level stuff, and you're not wrong. Creating an operating system is a seriously hardcore undertaking that requires a deep dive into the world of computer science, low-level programming, and the mysterious art of hardware management. But don't worry, we're going to break it down into manageable chunks and take it step by step. By the end of this video, you'll have a solid understanding of what it takes to create your very own OS from scratch. So, buckle up, smash that subscribe button, and let's get our hands dirty with some serious coding. Alright folks, before we even think about typing a single line of code, we need to make sure we're packing the right tools in our mental toolbox. Building an OS is like constructing a skyscraper. You need a strong foundation in the core concepts. First up, programming languages. You'll want to get very cozy with C and C++. Why? Because these bad boys give you the low-level control you need to interact directly with hardware. Think of them as the blueprints for your OS. Next, we've got computer architecture. You need to understand how the different components of a computer work together, like the CPU, memory, and storage. It's like knowing the layout of your skyscraper, where everything goes and how it connects. Then there's data structures and algorithms. These are the building blocks of your OS, the way you organize and manipulate data efficiently. Think of them as the beams and columns that hold your skyscraper up. And let's not forget about concurrency. This is all about managing multiple tasks running simultaneously, because an OS needs to juggle a lot of things at once. Imagine coordinating construction crews working on different floors of your skyscraper at the same time. It's a complex dance, but mastering concurrency is key to a smooth running OS. Lastly, we have the boot process. This is the sequence of events that happen from the moment you hit the power button to when your OS is up and running. It's like the grand opening of your skyscraper, where everything needs to come online in the right order. Understanding this process is crucial for bringing your OS to life. Now that we've got the knowledge locked and loaded, it's time to set up our development environment. This is where we'll be spending most of our time, so we need to make sure it's comfortable, efficient, and powerful enough to handle the task at hand. First things first, we need a trusty cross-compiler. What's that, you ask? Well, since we're building an OS, we can't exactly rely on our existing OS to compile it for us, right? That's where the cross-compiler comes in. It lets us compile code on one operating system like Windows or Linux that will run on a different target architecture, like our brand new OS. Think of it as building a miniature version of your skyscraper in a controlled environment before tackling the real thing. Next up, we'll need a virtual machine or emulator. This will give us a safe and isolated environment to test our OS without risking any damage to our main system. It's like having a virtual sandbox where we can experiment and make mistakes without bringing down the whole house. And of course, no developer's arsenal is complete without a powerful text editor or IDE, integrated development environment. This is where we'll be writing, editing, and debugging our code. Choose one that suits your style and workflow. Some popular choices include Vim, Emacs, Sublime Text, Atom, and VS Code. All right, folks, it's time to get our hands dirty and write some actual code. We're going to start with the bootloader, the tiny but mighty piece of code that kicks off the entire OS booting process. The bootloader is like the ignition system of your car. It's responsible for waking up the hardware and loading the operating system into memory. And just like you wouldn't want to mess with your car's ignition system without knowing what you're doing, we need to be extra careful here. We're going to be working with low-level assembly language, which talks directly to the hardware. Now, the bootloader has a few critical tasks to perform. First, it needs to initialize the CPU, setting up things like the stack and interrupt vector table. This is like making sure the engine is primed and ready to go. Then it needs to configure the memory controller so the CPU knows where to find everything it needs. This is like mapping out the fuel lines and air intake. Next up, the bootloader has to locate and load the kernel, which is the heart of our operating system, into memory. Finally, it hands over control to the kernel, marking the end of its short but crucial role. Think of it as the bootloader passing the baton to the operating system, saying, "All right, I've done my part, you take it from here." All right, we've got a bootloader up and running, which means it's time to tackle the heart of our operating system, the kernel. This is where things start to get really interesting. Think of the kernel as the brain of the OS, managing all the system resources and providing services to other programs. It's a big job, so we're going to break it down into manageable chunks. First up, we have memory management. The kernel is responsible for allocating and deallocating memory to different processes, making sure they have enough space to run without stepping on each other's toes. It's like a juggling act, keeping all those memory balls in the air. Next, we have interrupt handling. Interrupts are signals sent from hardware devices to the CPU requesting attention or reporting events. The kernel needs to handle these interrupts gracefully, responding to them quickly and efficiently. Think of it as the kernel being the ultimate multitasker, juggling requests from all over the system. Now let's talk about process management. The kernel is in charge of creating, scheduling, and terminating processes, ensuring that everything runs smoothly. It's like a conductor orchestrating the symphony of processes running on your system. And of course, we can't forget about file systems. The kernel provides a way to organize and access files stored on disk. It's like the librarian of your system, keeping all your data neatly organized and accessible. These are just a few of the core responsibilities of the kernel. As we add more features to our OS, the kernel will continue to grow and evolve. All right, we've got our kernel up and running, managing memory, handling interrupts, and generally being the boss of the system. But how do user programs actually interact with this all-powerful kernel? That's where system calls come in. Think of system calls as the official channels of communication between user programs and the kernel. When a user program needs to do something that requires the kernel's help, like opening a file or reading from the disk, it makes a system call. It's like sending a formal request to the boss. Now, system calls are implemented as special functions that user programs can call. The kernel provides a well-defined interface for these functions, so user programs know exactly how to use them. It's like having a clear set of instructions on how to submit your request to the boss. Some common examples of system calls include open, read, write, and exit. Open is used to open a file, read is used to read data from a file, write is used to write data to a file, and exit is used to terminate a process. These system calls are the building blocks for more complex operations, allowing user programs to interact with the hardware and the operating system in a safe and controlled manner. It's like having a set of tools that allow you to build anything you can imagine, with the kernel's permission, of course. Okay, we've got our kernel humming along, managing memory like a pro and handling system calls like a champ. But what about all the hardware connected to our computer? How do we get our OS to talk to the keyboard, mouse, display, and all those other essential peripherals? Well, my friends, that's where drivers come in. Drivers are like translators, allowing the operating system to communicate with hardware devices in their own language. Think of it like this. Your OS speaks English, your keyboard speaks French, and the driver is the bilingual interpreter that makes the conversation possible. Each hardware device typically needs its own driver, as they all have their own unique way of communicating. For example, the keyboard driver knows how to interpret key presses and send the corresponding codes to the operating system. The mouse driver knows how to track the mouse's movements and clicks. And the display driver knows how to draw pixels on the screen. Writing drivers can be a bit tricky, as it requires a deep understanding of both the hardware and the operating system. But it's also incredibly rewarding, as it allows you to unlock the full potential of your hardware and make your OS truly come to life. All right, we've got a kernel, we've got drivers, we've got system calls. Our operating system is starting to look like the real deal. But there's one crucial piece missing. A way for humans to actually interact with this technological marvel we've created. That's where the user interface, or UI, comes in. Think of the UI as the bridge between the complex inner workings of the OS and the simple minds of US humans. There are two main types of user interfaces: command line interfaces, or CLIs, and graphical user interfaces, or GUIs. CLIs are text-based interfaces where users type in commands to interact with the OS. They're powerful and efficient, but they can be a bit intimidating for new users. GUIs, on the other hand, are more visual, using windows, icons, and menus to make the OS more user-friendly. They're great for beginners, but they can be more resource-intensive than CLIs. Choosing the right UI for your OS depends on your target audience and the intended use case. For a simple embedded system, a CLI might be all you need. But for a desktop operating system, a GUI is pretty much a must-have. Now, building a UI from scratch is no small feat. It requires a deep understanding of graphics programming, user experience design, and a whole lot of creativity. But hey, we're building an OS here. We don't shy away from a challenge. All right, we've poured our hearts and souls into writing code, building a kernel, adding drivers, and maybe even creating a fancy UI. But before we pop the champagne and declare victory, there's one crucial step we can't skip: testing and debugging. Now, I know testing and debugging might not sound as glamorous as writing code from scratch, but trust me, it's just as important. In fact, I'd argue it's even more important. Because let's face it, no matter how good of a programmer you are, you're going to make mistakes. It's inevitable. And those mistakes can manifest as bugs, those pesky little creatures that can bring your OS crashing down faster than you can say segmentation fault. That's why we need to be vigilant about testing our code thoroughly, trying to break it in as many ways as possible. We need to think like our worst enemy, trying to anticipate every possible edge case and error condition. And when we do find bugs, and we will, we need to be prepared to track them down and squash them with extreme prejudice. Thankfully, we have a variety of tools at our disposal to help us with this task. Debuggers like GDB allow us to step through our code line by line, inspecting variables and memory locations, trying to understand why things aren't behaving as expected. Congratulations, you've reached a major milestone. You've built a basic operating system that can boot, interact with hardware, and maybe even provide a simple user interface. But the journey doesn't end here. Building an OS is an ongoing process of iteration and improvement. It's like raising a child. You nurture it, you teach it, and you watch it grow and evolve over time. And just like a child, your OS has the potential to learn and do amazing things. So where do you go from here? The possibilities are endless. You could start by adding more advanced features to your kernel, like multitasking, networking, and security features. You could explore different scheduling algorithms, memory management techniques, and file system implementations. You could even try your hand at creating your own programming language or virtual machine, all running on top of your custom-built OS. The key is to never stop learning, experimenting, and pushing the boundaries of what's possible. Embrace the challenge. Don't be afraid to make mistakes. And most importantly, have fun along the way. All right, you've poured countless hours into building your very own operating system. You've battled segmentation faults, conquered kernel panics, and emerged victorious from the depths of driver development. You've created something truly special, something that most people wouldn't even dream of attempting. And now it's time to share your masterpiece with the world. But before you unleash your creation upon the unsuspecting public, there's one crucial step. You don't want to skip documentation. Now, I know what you're thinking. Documentation? But that's so boring. I just want to write code. And I hear you. But trust me, documentation is essential. It's the difference between your OS being a hidden gem that only a handful of hardcore enthusiasts will appreciate and a shining beacon of innovation that inspires countless others. Good documentation explains how to use your OS, how to install it, how to configure it, and how to troubleshoot common problems. It's like a user manual for your brainchild, guiding others through the intricacies of your creation. And don't forget about the power of community. Share your code on GitHub, write blog posts about your experiences, and engage with other OS developers online. You'll be amazed at how much you can learn from others and how much you can inspire others by sharing your journey. Building an OS is a challenging but incredibly rewarding endeavor. Embrace the challenge, learn from your mistakes, and never stop pushing the boundaries of what's possible. So there you have it, folks. A crash course, pun intended, in building your own operating system. We've covered a ton of ground, from the absolute basics all the way to advanced concepts like drivers and user interfaces. And while this might seem like a crazy amount of information to absorb, remember, Rome wasn't built in a day, and neither are awesome operating systems. The most important thing is to take things one step at a time, don't be afraid to experiment, and most importantly, have fun along the way. Building an OS is a marathon, not a sprint, and it's a journey that's best shared with others. So get out there, connect with the amazing community of OS developers, and who knows, maybe one day your OS will be the one powering millions of devices worldwide. Building an OS is a huge undertaking, but with dedication and the right resources, you can create something truly amazing. Don't forget to document your journey and share your progress with the community. Happy coding!